I always needed a CNC milling machine, but for some good reason, I'm making one by myself instead of just buying one. And believe me, this is not just another DIY CNC video on YouTube. In this video, we dive deep and do reasonable things to achieve a valuable machine for the money and time we spend. I'm EK and you're watching Dynamic Systems. Okay, first question, why am I building this machine instead of purchasing one from the market? Well, if you look for a CNC machine to buy, there are two general types in terms of quality and price. First, we have the hobby machines, which are affordable, but they are nowhere close to the required characteristics for a clean job even on a hobby scale. Weak structure, which is also poorly designed, not even as rigid as it could be possible with the same material. Lead screws, linear bearings, weak stepper motors without encoders and heatsinks, cables without shields or anything to suppress electromagnetic interference, ultra-cheap electronics, very vulnerable to electromagnetic interference. DC motors for the spindle? No, sir, this is not how we work here. So we move on to the more serious industrial machines. We see there is a very desirable quality and capability out there, but for me and probably you, it's too much in every aspect. I mean, if I were even able to purchase their price, they are still big, complex, and expensive to operate and maintain. And I won't even use their full potential because it's beyond my needs. So I did much research and studied various subjects to design a machine to fill this gap for a good price, reasonable accuracy, rigidity, and power, and also practically possible to make using common and available materials and tools. I designed this, a 4-axis CNC machine with the minimum footprint to workspace ratio. One machine to cover all my milling and turning operations. One machine to do precision drilling. One machine to even grind surfaces.
One machine to laser cut and engrave. One machine to rule them all.
I designed this machine to be modular so it will be easy to build, assemble, fine-tune, and maintain. Let's check out the design on the CAD model. Base structure. The base structure is made of 80 by 80 square steel profiles with a 5 mm thickness. It weighs around 160 kg or 350 pounds. Although I outsourced this to be built by someone else, it came with awful welds and I had to do another layer of sturdy welding on it with the help of my friend. The profiles are quite rigid, especially with this truss structure, but I will fill them with maybe concrete or epoxy granite later. Obviously, the top surface of the base structure is not flat, and it's so big and heavy for any machining operation. I mean, it's not impossible, but it would be costly and difficult to transfer to another machining shop. So I applied a layer of epoxy on the top surface to let it get flat and level by gravity. Machine core, bed, and Y-axis. Here, the main challenge of all precision machines begins: having a real flat surface. The epoxy leveling gets us closer to a level surface. But in this step, we need a metal surface with maximum flatness to build our mechanisms on. I purchased 80 by 160 mm steel profiles, this time with 8 mm of thickness. I couldn't find the 10mm thick profiles, but if you found them, it's better to use thicker profiles. Then I cut it into
6
pieces with 900mm length. Using a heavy-duty metal bandsaw is recommended, but if you don't have access to it, you can try a metal chop saw like me. But you should be careful both about the safety and accuracy of your cut. 3 pieces are for the machine bed, and 2 of them are for the gantry y-axis, and there is 1 piece which we use for the x-axis. By grinding the surfaces of these pieces, we can get a big flat surface for the machine core first, and align everything parallel and square to the bed and achieve the precise geometry we need. The first 3 pieces get aligned to one surface when we bolt the other 2 pieces along the machine length. As both sides of the y-axis profiles are surface grinded, they are flat and parallel to the machine bed simultaneously. These y-axis profiles will be host the linear rails on the top side. If you grind the linear rail mounting channels, of course it will be better, but I couldn't find someone to do it for me because the grinding wheels are thicker than this 21mm wide channel. This is my own fault in terms of design, and I will improve it in the next version. The channel is 21mm wide. I can install 20mm linear rails easily and fix them with these horizontal set screws. Also, it's possible to adjust any imperfection in the machining of the channel if it isn't straight enough, just by placing some metal shims on one side and press it with the set screw on the opposite side. Gantry carriage blocks. I used the same channel technique for the gantry carriage blocks. They have the same set screw adjustments on one side, and this time I could grind the contact surfaces for these blocks, both on the top side and on the surface of the mounting channel. These blocks will host the linear blocks beneath them, ball screw nuts inside them, and the gantry on top. They are from regular structural steel alloys. However, I had to use this material because I couldn't find the alloy I was intended to use. Still, it's okay because these blocks are some sort of spacer and housing here that do not deal with the main stresses or vibrations. X-axis. The gantry. Here comes the
6th
profile piece as the gantry, and it's the housing of the x-axis of the machine. This piece has ground surfaces on all 4 sides, and they are parallel and perpendicular in pairs. This time I learned from Y profiles and changed the strategy of linear rails mounting channels to be able to grind them as well. But the set screw is gone and I need to add them using additional parts. Still not the perfect solution, but it should be fine. I use standard ball screw supports directly on the gantry profile, and here comes our
2nd
non-profile piece, the X-axis carriage sheet. This part is made from C45E alloy, also known as CK45, the alloy I wanted to use for the gantry blocks too. It needs to be ground on both contact surfaces, thermal stress relief, and vacuum thermal hardening using nitriding to achieve maximum strength and accuracy. I did it, it wasn't expensive and totally worth it. It houses the linear blocks of the X-axis and the ball screw nut and the Z-axis module. Z-axis. The Z-axis module starts with the same type of carriage as the X-axis, but this time the directions are different. There is a hole in both carriages which helps us during the assembly to lay the Z module's weight on a pin and proceed with the adjustments and fixing the module in place. The Z-axis itself is not made from profiles, it's another piece of CK45 alloy sheet. The same 30mm thickness, the same grinding, heat treatments, and nitriding process. To keep the linear rails straight in place, I added a side support sheet as well. This sheet will support the linear rails and add more rigidity to the Z module against torsional stresses and vibrations as well. Electronics. I guess it's enough for the overall review of the design here. So let me briefly talk about the electronics of the machine too, because it's just as important as the mechanical design of the machine to achieve our desired characteristics. Motors. Servo motors are too expensive for such a budget-friendly design. They also have their own domain of difficulty in installation and operation, better for fully industrial-grade machines, which I'm not able to purchase and have no reason to as well. On the other hand, we have the stepper motors with reasonably cheaper and enough torque for this machine, but they suffer from overheating and missing steps. That's one of the issues I mentioned earlier about hobby machines on the market, and it also doesn't fit with this design. But the third kind of motor that fits between is called easy servo, also known as closed-loop stepper motor. It's not a servo at all, it's a stepper motor which has an encoder on board and uses a different kind of driver that reads the feedback signal from the motor encoder to correct every missed step quickly and makes sure the positions are always correct. The additional benefits of these closed-loop stepper motors are that they work very smoothly, continuously, cool, and almost silently. So I use 4 of them, a pair for the gantry and 1 for each axis of X and Z. I also use separate drivers for each side of the gantry to adjust any misalignment between their positions in real time. Standard switching power supplies are also separate for each driver, so the chance of overloading will be minimized. Controller. I choose this CNC controller for my project. It's not sponsored. Actually, I had so much difficulty purchasing one set from China. Because, on this channel, I try to stay away from political issues, but I do need to point out So I had to spend $600 on this, and after 4 months, it finally arrived. But with a pair of components missing, it will be better to work flawlessly or things start to happen. Anyway, it supports 4 axes with 500 kHz for each, uses an ARM processor, an FPGA chip, LAN connection, USB memory port, able to operate completely standalone, lots of inputs for sensors, optional capabilities, and industrial stuff like that in a tiny package. So good stuff for my machine. Electronics cabinet. The electronics will be installed in this box, which includes 3 separated and insulated partitions. I arrange high voltage devices, power inputs, and lines separated from the low voltage side, using an MCCB switch and EMI filter for the main power input, dedicated MCB switches for each power supply. Pulse outputs, signals, and sensors have another separated side, with shielded cables and fried cores. The controller card and controller panel unit are placed here as well. The inverter has its own shielded partition, insulated again and equipped with another EMI filter to eliminate noise returning from the inverter to the power grid and reduce noise entering the inverter and all the other devices, and also a sine filter for the inverter output PWM current as well. It took me almost a year of research and design for this machine. And I hope all of these subjects I packed into my design will pay off in the final results. And a little surprise, this project is open source. So you can download the design and instructions to build another one for yourself. Thanks for watching and see you in the next one.